Hello, welcome to this 20-minute supplement on weight on Earth for the Gravitation and Black Holes course. The lecture script for all the supplemental videos is available at a link given in the description of this video. I will give attributions for images in the lecture script file. There are a number of interesting issues about weight on Earth. How does weight change based on where you are on Earth? Your altitude, the latitude, whether you're surrounded by air or water, buoyancy. How much is the force on a scale? How much does the atmosphere weigh? How much do you weigh while moving in an elevator? Why do you get hurt or die when you fall? How can you become weightless on Earth? How much is gravity inside the Earth? In the main course, we saw that the surface gravitational attraction for a spherically symmetrical mass distribution is gm over r squared. Earth is close to a sphere, but it is squished at the poles and bulging at the equator, closer to an oblate spheroid than a sphere. Capital G has this value, 6.67 by 10 to the minus 11 meter cubed per kilogram second squared. The uncertainty in Newton's gravitational constant is 22 parts per million, more than 100,000 times greater uncertainty than for the other fundamental constants of physics. Earth's mass is 5.9 by 10 to the 24 kilograms. Earth's equatorial radius is 6,378 kilometers. Earth's polar radius is 6,356 kilometers. Earth's standard gravity is taken to be 9.80665 meters per second squared. Earth's surface gravity decreases about 0.03% per kilometer of altitude or distance from Earth's center. You weigh slightly less cruising at altitude in an airplane than on the ground. Earth's surface gravity is about 0.5% higher at the poles, where the distance to the center of the Earth is less, than at the equator, where the distance is more. Since the Earth is not a completely spherically symmetrical mass distribution, scientists use more accurate gravity formulas that take the Earth's shape into account. But we will not cover this. Earth's acceleration and your weight depend very slightly on local conditions, whether you're on a continent versus on the ocean, near a mountain range, standing near a mountain of iron or copper, standing over an underground layer of oil or natural gas, etc. You can find more information at the Wikipedia article Gravity of Earth, including this gravity map accurate to parts per million. The Earth is spinning, and this affects what we measure as our weight and what we call the gravity of Earth. An observer not rotating with the Earth sees us Earthers experience a real centripetal acceleration toward the Earth's spin axis, not toward the center of the Earth unless you are at the equator, such that we match the Earth's rotation. Those of us rotating with the Earth perceive a centrifugal force outward from the Earth's spin axis. This reduces your measured weight, the ground contact force, by 0.33% at the equator. This reduction in your weight decreases with latitude until it is 0 at the poles. The inward centripetal acceleration and perceived outward centrifugal force associated with the Earth's spin produced the oblateness of the Earth when the Earth's mantle and crust was molten, then plastic, then solidified to its present shape. Our weight is very slightly affected by the tidal force from the Moon and the Sun, which is not included as the gravity of Earth. When the Apollo missions landed on the Moon, they did not land precisely where they intended. It turned out that the Moon is not sufficiently spherically symmetrical a mass distribution. To do precision landings on the Moon more accurately than the Apollo missions, future Moon missions need to use an accurate gravity map of the Moon, not the spherical idealization. Suppose you were responsible for an intercontinental ballistic missile program that needed the ability to precisely hit a target on the opposite side of the planet, and you wanted maximum possible accuracy of hitting your target. You should take an accurate gravity map of the Earth into account. Our weight is our mass times the local gravitational acceleration. Weight is downward force. When we are standing on the ground, our weight is balanced by an upward contact force provided by the ground. Our weight compresses the ground, which responds with the contact force. In English imperial units, we measure weight in pounds, which is really pounds force. In SI scientific metric units, weight should be measured in newtons, the force unit, but weight is typically given in kilograms, so mass, not weight. In English units, pounds is force, and slugs is the unit of mass, which American mechanical engineers used to use in their calculations. As we stand on the surface of the Earth, we are surrounded by Earth's atmosphere, not the vacuum of space. The atmosphere has weight, and we experience a slight upward buoyancy force due to being surrounded by air. Air pressure varies and is part of weather conditions. At one standard atmosphere of pressure, the atmosphere presses on the surface of the Earth with a pressure of 101 kilopascals, or 14.7 pounds force per square inch, psi. This pressure presses down on the scale we use to weigh ourselves, and the ground provides contact force to match it. But the scale is designed to display this amount of force as 0. When we stand on the scale, our body displaces our body volume of air that previously was pressing on the scale. Air density at sea level is about 1,000th of our body density, so our weight in vacuum would be 0.1% higher than our buoyant weight in air. Buoyancy in air is minimal, but not so in water. Our bodies are mostly water, but bone and muscle are denser than water, and body fat is less dense than water. Some people float easily and others sink. Scuba divers use weight belts to maintain neutral buoyancy underwater. One atmosphere of air pressure also equals the pressure we would get from a 30-inch or 760 millimeter high column of mercury, or 33 feet of water. Underwater, pressure increases by 1 atmosphere for every 33 feet you descend. Weightlessness is the state of accelerating in free fall due to Earth's gravitational acceleration and Earth's spin with zero contact force. Life on Earth developed in Earth's gravity. Humans and some organisms do surprisingly well in weightless conditions, though our stomachs do not like it at first, and we may be nauseous or airsick. There are several ways of achieving weightlessness on Earth, on and near the Earth. We could fall freely from a height or jump out of an airplane. We would be briefly weightless when we jump, but not once air resistance retards acceleration and not at terminal velocity. We could drop an object in a vacuum column to get rid of air resistance. We could fly in NASA's Vomit Comet airplane, which gives 25 seconds of weightlessness as the plane executes a downward-facing parabolic flight that matches gravitational freefall. The plane executes 40 to 60 weightless maneuvers per flight to train astronauts or to film weightlessness for movies such as Apollo 13. We could take a roller coaster designed with a downward-facing parabolic path to produce some amount of weightlessness. We could build an elevator to descend at 9.81 meters per second squared, downward acceleration, for a few seconds, but ordinary passengers would not like being weightless. We could take an orbital or suborbital spaceflight. Once the rocket thrust ends, we would be in freefall and weightless. We could go to the International Space Station or the Chinese Space Station. Astronauts there are weightless due to the free fall acceleration of their orbits, not due to their altitude and gravity decreasing with altitude. A scuba diver may be neutrally buoyant and their weight is offset by the water, but this is not really weightlessness and stomachs don't mind it. Likewise, for exercising in a swimming pool to offset weight, to exercise joints safely. NASA uses deep water pools to train astronauts in full spacesuits. They're not weightless, but their weight is offset. There's no contact force on their feet, and they can move around free from the ground, though they're hampered by water viscosity. How much do we weigh in an elevator? If the elevator is moving at a constant speed, or not moving at all, our weight is the same as on the ground. If the elevator is accelerating upward, our weight is increased by the acceleration amount times our mass. If the elevator is accelerating downward, our weight is decreased by the acceleration amount times our mass, which may be uncomfortable in a skyscraper elevator. Why do you get hurt or die when you fall? You get hurt when you decelerate rapidly when you hit the ground. The force on you is your mass times the deceleration. If you land on hard ground or belly flop onto water, the deceleration can be much higher than the acceleration of gravity and can break bones or kill you. If you land on something that is compressible, like a foam mat, your deceleration is greatly reduced. How much is gravity inside Earth? Gravity increases as distance decreases, right? Well, that formula is for gravity outside the gravitating body, not inside. In this formula, capital R should be lowercase r. If the object is a spherically symmetrical mass distribution of capital radius r, then the gravity at radius lowercase r less than capital R is this formula. Where capital M of R is the amount of mass contained inside the sphere of radius lowercase r. We can use the formula for mass being volume times density, and we get that gravitational acceleration as a function of radius is 4 pi g over 3 times the density times the radius if the spherical object has constant density. If the sphere were to have constant density, then gravitational acceleration would be linear with radius as we go into the object, from 0 at the center to the surface value at the surface. This may seem surprising at first. Why is there no gravitational force at the center of the sphere? Spherical shells produce no gravity inside the shell. This does not mean that nothing is going on at the center. Pressure from higher layers increases with depth and is highest at the center, about 3.6 million atmospheres at the center of the Earth. At any radius, pressure from below balances weight pressure from above such that there's no motion. The situation is static. The core of the Earth provides outward pressure due to compression of the core from the weight pressure from above. The core of a star provides outward pressure due to the high temperature resulting from nuclear fusion in the core, which only occurs at high pressure and temperature. Planets and stars do not have uniform density. They are denser at their cores and least dense at their surfaces due to gravity and pressure. The Earth's average density is 5.5 times the density of water, higher than the density of the rocky mantle and less than the density of the iron core. As we descend from the surface of the Earth, gravitational acceleration increases slightly at first, because the density of the crust and mantle are less than the average density of the Earth. Lower down, we see the nearly linear relation. Here is a graph of calculated density inside the Earth. Here's the surface. Density increases. The density of rock is higher than water. As we go in, the density continues to increase. The rock is under pressure. And we reach a point where rock is above and iron and nickel are below, and they have a higher density. And as we move deeper in the core, the pressure compresses the core more and more, and the density increases until we get to the center of the Earth. The density of iron at Earth's surface is about 8,000 kilograms per cubic meter, about this level. It is compressed in the Earth's core.